Alright guys, so in this set of videos, and there's going to be more than one, I'll go ahead and tell you. So in this set of videos, we're going to talk about this word called stoichiometry. And we rarely have to use this to make samples or to make standards or solutions. However, we do have to use it in a laboratory when we work with standards or solutions. And it basically is just a fancy way to describe how we can relate one molecule or substance to another. So it's a way that we can compare. If we start off with this reagent or this sample or this solution and we end up with this one, how can we relate those two species together? Now, the reason that I'm talking about it is because this is pretty important in a laboratory field, right? And I can't really take advantage of Chemistry 151 or 152 teaching you stoichiometry and everything that you need to know about it maybe the first time that you go through it. And because of that, I just kind of want to take a step back and I just want to review stoichiometry if you've taken those classes so far, so that way we're all on the same playing field. Because this is one of those staples that you should take away if you're going to be working in a laboratory environment. You've got to be comfortable with stoichiometry, how to calculate theory yields, how to calculate percent yields. And that's what this whole lecture kind of combo is going to do. So I first want to start off with an equation, all right? And this equation, because we're talking about basic chemical calculations here, right, looks like C2H5OH plus 3O2 should give me 2 CO2s and 3 H2Os. Now, this is a chemical equation, right? And what this equation does is it's going to take this molecule, C2H5OH, which is ethyl alcohol, and it's going to react it with O2 gas. And a combustion reaction is going to happen, and it gives me CO2 and water as a product. Well, what stoichiometry does is if it says, if you start off with this much alcohol, ethyl alcohol, C2H5OH, how much water could you end up with, right? Or if you start off with this much alcohol, C2H5OH, how much CO2 could you end up with? That could be a question. Well, I could do the same thing with the O2s, right? If you use this much O2, how much water could you end up with? That's a relationship that I could bring out from the equation. And another relationship that a lot of people ignore is if I use this much alcohol, how much O2 do I have to react with it in order for this reaction to go forward to make sure I have enough? Basically, bottom line, stoichiometry allows you to compare two things together. Any two things is fair game. As long as you're comparing two things together in the reaction, you can use stoichiometry in order to do what you need to do. Now, to do that, we need something called a mole ratio. And a mole ratio is the number that we use in our dimensional analysis. All of these setup problems that we've been doing, we use the mole ratio in order to help us determine what our answer is going to be. The mole ratio, well, it's pretty simple. It comes from a balanced chemical equation. Now, that's the key word. It has to be balanced. Now, we are not talking about how to balance equations here. That should be taken care of in 151 and 152. So all of these reactions that you're going to be given, they're already going to be balanced. You don't have to worry about that. The only thing I want you to focus on is relating two species together, bottom line. All right? So it comes from the balanced chemical equation, and it's basically the numbers that are in front of these things that I want to compare, right? So here we have a balanced chemical equation. Well, there's no number here in front of ethyl alcohol, C2H5OH. Well, it's understood to be a 1. And then here we've got a big 3, and here we've got a big 2, and there we've got a big 3. That's what we're after. That's what we need. That's where the mole ratio is going to come from. Now, let me show you how to use it. The key part to stoichiometry. Let's say, in our first example, that we have 3 moles of C2H5OH. How many moles of H2O could it make? The reason I said make is because H2O is a product. That's what it's making, right? So if this is my starting amount, how much could I end up with? Very often you might hear people describe this in terms of sandwiches in a Chemistry 151 class, right? They'll go through this description and they'll say, well, imagine that you've got this number of pieces of bread and this many pieces of lunch meat and this many pieces of cheese, and you want to make a sandwich, and to make a sandwich you need all these pieces together, and this is how many bread and lunch meat and cheese slices that you need to make one. Which one you're going to run out of first? That's the whole description that they start talking about. I don't want to talk about sandwiches here, people. I want to talk about chemistry. I want to talk about lab, right? So if I have 3 moles of C2H5OH, how many moles of water could I end up with, right? This is my starting product. How many could I end up with in the very end? This is how we do it. I take my given, 3 moles, just like before, just like in every single problem that we've done so far. C2H5OH over 1. Bring in your dimensional analysis step. Mole of C2H5 on top, mole of C2H5OH on the bottom. Well, this problem tells me I need to relate it to mole of water. So mole of H2O goes up here on the very top. That's the whole power of stoichiometry. It allows me to relate mole of one substance to mole of another substance. There you go. Well, what numbers get plugged in here? That's the mole ratio. That's what we just talked about. That mole ratio, well, if I go up to the equation, C2H5OH, here's my C2H5OH. There's a 1 out in front, so I put a 1 there. Here's my mole of water. There's water. There's a number in front. There's a 3 there. There's the mole ratio, people. That's all we need. It's as simple as that. If the equation's already balanced, all of the pieces of the puzzle are there. You just got to be able to plug them in the right way. So, to solve this problem, I'll take 3 moles and I'll multiply it by 3, and 3 times 3 is 9. So, it will make 9 moles of water for me. Now, we can relate this to gram, we can go to milliliter, we can do all kinds of crazy stuff. That's not what the purpose of this video is. It's getting comfortable with the concept of bringing in the mole ratio. What information is the equation trying to present to me so I can do these calculations the way that I need to do them? This is how we do it, all right? So let's try another example. This time I'm going to change the color so it doesn't bleed in together. Let's say that we have 6 moles of O2. I want to know how many moles of CO2 could I end up with, right? If I had 6 moles of oxygen and everything else I have plenty enough of, how many moles of CO2 would I end up with after this reaction's over? All right, well, I do that just like I did up above. 6 moles of O2 over 1. Mole of O2 on top, mole of O2 on the bottom. And they want me to go to mole of CO2. I can do that. I can go from one compound to another as long as I have the mole ratio from the equation. So up here in the equation, the O2 has a big fat 3 out in front, so the 3 goes there. And the CO2 has a 2 out in front, so a 2 is going to go there. There's my calculation. So I'll take 6 and I'll multiply it by 2 and I get 12, and then I divide that by 3 because that's on the bottom, and I get a total of 4. So 4 moles of CO2 is what I would have. Okay? It's as simple as that. That's all that stoichiometry is. Everything else that will follow suit will have already been discussed in the previous videos. This is the only extra step that we're bringing into the picture. And that's it. That's all there is, folks. Stoichiometry does not have to be harder than this. All right, so I'm going to go back to this roadmap. And we said that we can go from gram to mole as long as we know the formula weight in order to get there, right? And we said that we can go from mole to molecules or ions or to atoms as long as we know Avogadro's number. Well, I'm going to put a little a here and an a there and an a there, meaning one compound that I'm using from the reaction, doesn't matter, it's all the same. I can go grams of alcohol to moles of alcohol to molecules of alcohol. Grams of CO2 to moles of CO2 to molecules of CO2, right? And if there's something else that I'm kind of wanting to pay attention to in the reaction, another type of compound, I can do the same thing up here. There's no big deal, right? I can go from grams of another substance to moles of that substance to molecules of that substance. I use the same numbers. No difference. And up until this point, we've had no way to connect them together, right? Let's say this represented the ethyl alcohol or the ethanol in that equation, and this up here represented the CO2 in that previous equation, but there was no connector piece. I could go from grams of alcohol to molecules of alcohol if I go through the proper steps. I could go from moles of CO2 to molecules of CO2 if I go through the proper steps, but there was no way to connect the pieces, and stoichiometry does it. Stoichiometry is the connecting piece, and the only way that you can connect them is right here between the two moles of substance. That's all. So that's a route now that you can take. Those two roads will join. They will come together, but it will only come together at that intersection. If you miss that intersection, you're going to have to turn around and come back, because there's not going to be another intersection that will connect the two for you. And that connector is the mole ratio. That is coming from the balanced chemical reaction. That's all there is. That's all there is to it. So as long as I have the balanced chemical reaction, I can do these calculations. Nothing else is new in stoichiometry world. I know that these problems will eventually seem like disaster on wheels. However, keep that in mind. Stoichiometry is just one little bitty step. That's it. And it connects the two products or reagents, or one product and one reagent, two things together. That's the only purpose of it. That's it. All right. So that's where this video is going to stop. In the next video, we're going to go through and we're going to do some examples. We're going to work through some equations and work through some examples to try to get a better feel of what they're after. So that way I can go through and maybe bring in grams and bring in molecules and bring in these other conversions that we need. But hopefully now you're going to see that this isn't as complicated as what it needs to be. So take a break, come back within a couple of minutes. You're on a roll. Don't lose me now. And then we'll talk about these examples and how to solve these types of problems.